Section 5. The Next Great Mystery. So, Einstein was definitely wrong to doubt his own math.
So imagine you create a theory so breathtakingly beautiful that it completely rewrites the laws of the universe. But then you discover a terrifying, apocalyptic mathematical anomaly hiding deep inside your own equations. An anomaly so seemingly impossible that you actually spend years trying to prove your own math wrong. In this explainer, we're diving into exactly that, how Albert Einstein's majestic theory of general relativity was nearly destroyed by a mathematical monster he inadvertently unleashed.
Seriously, what actually happens when a scientific genius finds a monster in his own math? Well, let's trace the dramatic journey of an idea that completely turned 250 years of established physics entirely on its head, and in the process, reshaped our fundamental understanding of reality. Section 1. A New View of Gravity. To really appreciate this, think about the sheer contrast and how we used to view reality. For centuries, Isaac Newton saw a universe with perfectly straight space, all governed by one huge, ticking universal clock. But Einstein, he envisioned something radically different. He saw a four-dimensional geometry where space and time are deeply intertwined, literally woven together into a single fabric. And you know, it actually all started with a simple yet profound thought experiment. Picture Einstein sitting at his desk at the patent office in Bern, back in 1907. Suddenly, it hits him. Gravity has a highly unique property. It vanishes as a result of its own effect. Meaning, if you are in free fall, you wouldn't feel your own weight. This incredible spark of genius became known as the principle of equivalence. To wrap your head around it, think of space like a giant block of jelly. The presence of massive matter like planets or stars distorts and curves that jelly. And we can actually test this free-fall idea today. Inside a 110-meter drop tower in Germany, scientists create 5 seconds of vacuum free fall, dropping a 1 kilo weight and an apple. On the way down, the scales just drop to zero. The mass seemingly disappears, all because the objects are simply following the naturally curved, jelly-like fabric of space-time. This is huge for us because it proves gravity isn't some invisible magnetic-like pull. It's simply the shape of the space we live in. Section 2. Proving the impossible. Now, getting to that realization was a rapid, intense journey. Believe it or not, Einstein's own math skills weren't quite enough to get him over the finish line. He had to rely heavily on his old friend Marcel Grossmann's geometry expertise in Zurich to finalize his wildly complex equations in 1915. He immediately used them to perfectly solve a lingering mystery regarding Mercury's orbit. Then, in 1919, a British pacifist named Arthur Eddington traveled to photograph an eclipse, proving definitively that the sun's mass actually bends starlight. That was the moment. It catapulted Einstein to global fame and a well-deserved Nobel Prize in 1921. So after 8 years of just monomaniacal work, we get this one elegant equation, and it revealed a truly mind-bending reality. Gravity actually slows down time. The stronger the gravitational field, the slower time passes. And guys, this isn't just theory. It is proven today by hyper-precise atomic clocks sitting right now in the basement of the Observatoire de Paris. The universe absolutely does not tick to Newton's universal clock. Every region, every single pocket of space has its own time. Section 3. The mathematical monster. But right in the middle of this massive triumph, things got really weird. It's 1916, World War I is raging, and a physicist named Carl Schwarzschild manages to solve Einstein's complex equations for a star. It was a titanic mathematical achievement, but Schwarzschild inadvertently discovered a fatal flaw. He found it placed at the center of the mass where the very concepts of space and time no longer made any logical sense whatsoever. And the academic world definitely noticed. Jump to a 1922 conference at the Collège de France in Paris, where mathematician Jacques Hadamard dramatically confronted Einstein. He pointed out that at a certain radius in Schwarzschild's solution, the equation literally dictates that you divide by zero, yielding infinity. Mathematically speaking, it was the end of the world in equation form. So how big is this mathematical monster? Well, it depends on the mass of the object. For our sun, the math dictates that this singularity is exactly 3 kilometers wide, hidden deep inside the star's core. For this impenetrable black bubble to actually become visible, you'd have to condense the entire mass of our sun down into a tiny sphere just 3 kilometers across. Einstein found this totally unbearable. I mean, the idea of stars imploding into an infinite singularity repulsed him so much that he set out to definitively prove it impossible. He ended up writing what is widely considered his worst scientific paper ever. He used flawed, backward logic, actually starting with the conclusion he wanted to reach, just to try and disprove the physical reality of these singularities. Section 4. Discovering real black holes. But, as it turns out, the universe is far stranger than Einstein wanted to believe. Astrophysicists soon began to understand the true life cycle of massive stars. When a huge star runs out of nuclear fuel, gravity wins the battle. The core collapses dramatically. Now, often this leaves behind a hyperdense neutron star just 10 kilometers across. But if the star is massive enough, the collapse doesn't stop. It shrinks right past the point of no return, collapsing all the way down to zero radius, a black hole. Then, in 1967, theoretical physics met hard, undeniable observational evidence. A young scientist named Jocelyn Bell Burnell was working with freezing radio telescope equipment at 2 in the morning, and she discovered an entirely new class of object. She detected a curious signal pulsing exactly 1 1/3 seconds apart. She had discovered pulsars, spinning neutron stars. This proved once and for all that these extreme, hyperdense stellar remnants absolutely do exist in the real universe. If you want to grasp just how extreme these objects are, imagine actually visiting a pulsar or a black hole. The gravity is so immense that there's a massive gravitational gradient. The pull on your feet would be vastly stronger than the pull on your head. This leads to a gruesome scientific concept actually termed spaghettification. Your body stretches exponentially until your feet are physically pulled off your legs and your head separates from your body, dropping onto the star piece by Rose is literally just crossing a street when he has a sudden epiphany, formulating the math to prove definitively that the singularity is real. At the center of a black hole, the fabric of space-time actually tears. This leaves modern titans of science, like the late Stephen Hawking, grappling with massive consequences. Think about it. If a black hole swallows matter, is that information lost to the universe forever? It's a deeply debated mystery that absolutely requires us to somehow merge quantum mechanics with general relativity. And it gets even crazier. Physicist Carlo Rovelli suggests a fascinating theory called loop quantum gravity. His calculations propose that black holes don't actually stay collapsed forever. Instead, they compress into a tiny Planck star, and then, very quickly, bounce out and explode. But here's the catch. Because extreme gravity drastically slows down time, that tiny millisecond rebound on the inside looks like it's taking billions and billions of years from our perspective on the outside. We are essentially watching an explosion happen in extreme slow motion.
You know, towards the end of his life, Isaac Newton beautifully captured this exact feeling of scientific discovery. He compared himself to just a boy finding pretty shells on a beach. Einstein recognized this exact same reality too. His beautiful equations were really just a few pretty shells, while an immense dark ocean of things we have yet to understand lies completely undiscovered before us. So I want to leave you with this final, truly mind-bending thought for this explainer as we try to move beyond Einstein. The new loop quantum gravity equations that physicists are using to merge relativity and quantum mechanics have something very, very strange about them. They contain absolutely no time parameter, none. If time isn't actually a fundamental ingredient of the universe, then what exactly is the passage